Stepper motor is electromagnetic incremental devices that convert electrical pulses to shaft motion. Unlike a conventional electric motor which rotates continuously, this motor rotates a specific number of degrees as a response to each input electric pulse. The typical type of stepper motor that can rotate an angle of 2 degree, 2.5 degree, 5 degree, 7.5 degree, and 15 degree are commonly available. This motor is popular in many applications where power range is not high, such as robotics, printers, disk drive, and control application. The main feature of this motor is inherently position control without any closed-loop feedback, and hence this motor is used where we need precise position or angular control. This motor is classified into 3 categories. First, permanent magnet stepper motor, in which permanent magnet is used in the rotor. Second, variable reluctance stepper motor where soft iron material is used in the rotor. And third, hybrid synchronous stepper motor that combines the features of both the rotors. The stator of these motors is made of laminated thin sheets to reduce eddy current. Let's understand how the permanent magnet stepper motor converts electrical pulses to angular rotation. Let's take an example where the stator has got 4 poles and the rotor has got 2 permanent magnet poles. The stator pole has concentric winding, where winding A is connected to A prime, and similarly winding B is connected to B prime. When winding A is energized, or in other words current is injected into the winding, south pole is created under that pole. At the same time current is leaving from the A prime winding, and hence N pole is created under that pole. The same is applicable to winding B and B prime. The stepper motor can be controlled by energizing every stator phases sequentially. From the rotor position shown in the figure, if we excite the winding A, S pole is generated under the A winding, and at the same time, N pole is created under the A prime winding, as current is leaving from the A prime winding. In this situation, north pole of the rotor attracted by the south pole of the stator, and south pole of the rotor attracted by the stator N pole. Hence, rotor travels 90 degrees to attain equilibrium position. After 90 degree rotation, winding A is energized and winding B is energized, and rotor travels another 90 degrees in clockwise direction. Now in this rotor position we excite the A prime winding, and current is injected into the A prime winding, and hence S pole is created under A prime and N pole is created under A winding. Rotor travels another 90 degrees. Finally B prime winding is excited, and rotor completes its full 360 degree rotation. This is how permanent magnet rotor rotates. For anti-clockwise rotation sequence of switching should be reversed. A simple circuit arrangement for supplying current to the stator coil in proper sequence as shown in this figure. The transistor Q1 and Q4 are turning on to create S pole under the A winding. The stable rotor position as shown is considered as reference 0 degree position. Note that the positive excitation of a winding is considered as 1 in the truth table, and negative supply of a winding will be termed as -1. To excite the winding B, the transistor Q5 and Q8 is turning on, and create S pole under the B winding, and N pole under the B prime winding. Now to create S pole under a prime winding, transistor Q2 and Q3 are turning on. This will result in reverse excitation. And finally Q6 and Q7 are turning on to generate S pole under B prime winding. After every excitation, rotor rotates 90 degrees called step size. The step size can be reduced by increasing number of stator poles. Permanent magnet has mechanical constraints, and that why the available range is limited to around 30 to 90 degree only. Due to permanent magnet rotor, inertia is very high, and so poor speed response is recorded. The maximum pulse rate is also limited to 300 pulses per second. It means that the motor we discussed takes 4 pulses for 1 revolution, so maximum 75 RPM could be achieved by that configuration. This motor will generate high torque due to permanent rotor. In case of stepper motor, variable reluctance or hybrid configuration is more popular. I hope you like this video. Press the bell icon to subscribe our channel.